Hello, everyone. I present AutoAWG, a framework for adverse weather generation in autonomous driving videos. It addresses the critical data scarcity problem that limits perception under harsh weather. Rain, fog, snow, and nighttime severely degrade driving perception. Perception models trained on clear weather suffer significant performance drops. Collecting real adverse weather data is dangerous, expensive, and hard to scale. Yet without such data, models cannot handle safety-critical scenarios. AutoAWG solves this by generating realistic weather videos as plug-and-play training augmentation. Our core idea uses a coloring book metaphor. Given a clear weather driving video as input, we extract three structural conditions as outlines. A weather condition diffusion model then paints adverse weather onto these guides. The conditions control how much structure is preserved, while the model adds realistic weather appearance. We use three conditions spanning a control spectrum. Lineart captures the finest structural details, down to tree bark textures and lane markings. It enforces the strongest structural constraint. Depth captures coarse, three-dimensional layouts, with the weakest structural constraint. Sketch sits in between, retaining shape while allowing texture variation. Different scene regions need different control strengths. A segmentation mass partitions each frame into sky, road, vehicles, and pedestrians. Vehicles and pedestrians receive lineart, the strongest control for structural preservation. Sky receives only depth, the weakest, for free weather texture painting. This adaptive fusion preserves safety-critical objects while allowing realistic weather generation. We introduce an importance-weighted loss. Standard training treats all pixels equally, but vehicles and pedestrians matter more than background fine details. We add extra weight on object regions. Guided by the object, mask M. Our ablation confirms. Detection map improves from 0.6394 to 0.6594, while weather realism is maintained. Data is the fuel for generative models, but adverse weather driving videos are scarce. We propose VP-anchored temporal synthesis. The AC/DC dataset has 4,006 weather images, spanning fog, rain, snow, and nighttime, but they are static, no temporal information. We estimate each image's vanishing point, then perform progressive cropping, while keeping the vanishing point fixed. Crops are concatenated into 45-frame videos, simulating stable forward driving motion. Here are our AC/DC pseudo-video results. 3 examples from different weather types. AutoAWG extends to multi-camera systems. Autonomous vehicles carry multiple cameras, covering a 360-degree field of view. We stitch all views into one composite grid. Self-attention captures cross-view consistency. Here are multi-view results under rain. Notice, all 6 cameras show consistent rain. Fog conditions. Same fog density across all camera views. Nighttime conditions. The same vehicle appears in adjacent views, with consistent color and lighting. Snow conditions. Cross-view consistency is excellent. No visual seams between cameras. All views maintain unified weather appearance. Objects share identical style across cameras. For long video, we use segment-wise generation. During training, we randomly mask frames to learn both first segment and continuation. At inference, each new segment is conditioned on the last frame of the previous segment. This ensures smooth temporal continuity, with no flickering or style drift. The result, stable quality over hundreds of frames. Now let's look at quantitative results. We compare on the nuScenes validation set against several state-of-the-art methods. Without first frame guidance, we achieve FID 12.5 and FVD 79.4, already competitive with prior methods. With first frame guidance, FID improves to 6.3, FVD to 51.7, substantially surpassing all baselines. More importantly, for downstream tasks, we train BEVFusion on our augmented data. MAP improves by 1.99, NDS by 1.36. Our generated videos deliver tangible benefits. For real-world perception algorithms, we evaluate edit fidelity, how well-seen elements are preserved. Our map drop is only 0.0177 after weather transfer versus 0.1736 for Magic Drive V2. The same scene transformed into fog, rain, snow, and nighttime. Vehicles, pedestrians, and traffic signs are nearly perfectly preserved. Weather effects appear realistic and natural. We compare against image-level methods, GCHQ and QTNet. Despite never training on cityscapes, our model produces high-quality weather effects. Against video methods Vista and Panacea, we generate more realistic traffic elements. Vista and Panacea show artifacts and structural inaccuracies. We also generalize robustly to B2D100K without any training on that dataset. For long video stability, from first to last segment, FID rises by only 8.4, FVD by 64.4. GEM degrades by 19.2 and 208. Vista degrades by 28.1 and 259. Now watch our full long video demo. Over 250 frames, no flickering, no color drift, no quality degradation. Weather style remains perfectly stable. Another sample, different weather, same stability. Temporal consistency is maintained throughout. In summary, AutoAWG offers 3 advantages. First, high-quality generation through adaptive control fusion, an importance weighted loss. Second, high consistency. Generated videos reuse original annotations. For plug-and-play data augmentation. Third, high flexibility, supporting multi-camera systems and arbitrary-length video sequences. Code and models are fully open-sourced. Thank you. We welcome your questions.